Ugh, I'm so hungry.
Me too.
I don't want to wait for food to get here.
Alright, you know what, let's just cook dinner by ourselves.
That takes so long. What are we going to cook?
We can just cook an egg. It'll take like 2 minutes.
You know, I'll get the pot ready right now.
How do we get this thing out of its shell?
I don't know.
Oh, why don't we try dissolving it?
That's not how it works.
Yeah, it is. I read it in an article. Excuse me, just put it in.
Okay.
I'm sorry.
I don't feel it.
It's not doing anything.
Why isn't it doing anything?
So dumb. Why wasn't the egg dissolving?
I don't know. Well, to understand that, we have to define solubility first.
The solubility is the ability of a substance to be dissolved in water.
In other words, something that's soluble will break apart when you put it into water.
An example of a soluble compound would be salt or sodium chloride. See?
When you put it in, all of the salt will dissolve into an aqueous solution.
That means all parts of the solution are going to be equally homogeneous in how much salt is in the water. There are a few things that are always soluble. Any salt of an alkali metal, a nitrate, or ammonium will dissolve in water no matter what it's paired with. Now that we've established all the compounds that are always soluble, which are salts of alkali metals, ammonium, and nitrates, let's talk about compounds that are insoluble except for those rules that we've already established. These following compounds are always insoluble except for those rules that we've already talked about. Those are phosphates, carbonates, and oxides, although oxides are very rarely in any solution. So, insoluble really means it won't break apart. So let's do a demo. Cell phones are probably insoluble. Let's try. Not soluble, see? There's no dissolving going on. Now let's talk about the salts of the halogens, chlorine, bromine, and iodine. All of them are going to be soluble when paired with anything.
Well, you're wrong.
What do you mean?
These substances are not soluble. They're exceptions. Mercury, lead, and sulfur.
So you're saying whenever those are joined with any of these, they're not going to be soluble?
And plus, they form precipitate, you know?
Oh, I see.
Yeah, so
what is this you drew here?
I've created a mnemonic device.
Uh-huh.
Holy girls play baseball angelically and gracefully. So look at this picture.
That's perfect.
I know, you'll remember it so well.
Remember, mercury, lead, and silver are going to form solids when paired with any of the halogens.
Now let's talk about other substances, such as sulfates and hydroxide. Sulfate, Sp2-, is all soluble, and hydroxide, OH-, are also all insoluble.
Now that's just not true. There's a few exceptions for that for this too. And I brought my mnemonic device this time. As far as sulfates go, all of them are soluble except for these: strontium, barium, and calcium. And all hydroxides are insoluble except for the same three elements.
What's this drawing then?
This drawing is strong rhinos battle against clever anacondas.
Now I get it.
Solubility is most important in double displacement reactions because that's when precipitate might occur.
A precipitate is when two aqueous or soluble compounds are in a double displacement reaction, and in that process, an insoluble compound is formed, and therefore would be solid in solution.
So let's do one example problem of this. So, number 1. Let's assume that it's potassium chloride in aqueous solution plus sodium nitrate in aqueous solution, which yields to,
in this case, potassium nitrate in aqueous solution and sodium chloride. So now that we've seen an example of a reaction that won't form a precipitate, let's look at one that will.
Alright, example number 2. Sodium iodide in aqueous solution plus lead nitrate in aqueous solution yields to sodium nitrate in aqueous solution plus lead iodide as a solid.
So, in net ionic form, which hopefully you've learned already, All the ions that don't form any precipitates are just going to not be in the reaction.
Because they're spectator ions.
They don't do anything. But here, we have iodide ions and lead ions forming lead iodide, a beautiful yellow compound that you're about to see.
Adding very pale yellow sodium iodide to colorless lead-2 nitrate produces a yellow precipitate.
So now, let's solve the mystery. Why didn't the egg dissolve?
Well, I did some research, and it turns out eggshells are made of calcium carbonate. Didn't we learn something about carbonates?
I think all carbonates are insoluble.
That's right, and that's why the shell wouldn't dissolve.
Yay, we solved the mystery.